Welcome back. We're now going to talk about square roots, and then we're going to focus in on a preview of completing the square. Next week is going to see us grapple with that before we finally get the quadratic formula. So square root property is if I have a variable or a thing squared that's equal to k, a number, then I know the solutions must be either x is the square root of k or x is the negative square root of k. So we sometimes write that as the plus or minus square root of k that you're familiar with by now. So x equations plus or minus the square root of k. I don't think that's the way it's read. Is x equals plus or minus the square root of k? All right. So we are going to explore the various ways that this property can be used. So the big idea is I need a squared thing isolated on one side and just a number on the other side, and I can apply the square root to both sides. The catch is when you apply a square root, you have to remember that it gives you two answers, a plus and a minus. So here, x squared minus 25. Now we do know this factors, but here's another way to solve it. And this works for ones that don't factor so nicely. So we have the squared thing isolated. We have just a number on the other side. So now to get rid of the squared on the x, I'm going to apply the square root to both sides. Here, the square root and the squared cancel each other out like we saw with the radicals last week. Whatever I do to one side, I do to the other, with the caveat that one of the sides needs a plus or minus. And you can split it right then as x equals or x equals positive square root of 25, x equals negative square root of 25, and then go from there. And there's some problems where that may be beneficial. Here, just going to be lazy. Plus or minus and square root of 25 is 5. Now on ALEKS, unless there is a plus or minus button, you're probably going to have to do a list. So 5 comma negative 5 or negative 5 comma 5. Just remember no parentheses around it. But for doing handwritten work, this is often what people accept. All right, same song, second verse. We're going to minus that 48 over. Ew. Why am I making funny noises? All right, and then our next step would be and woo. Ruh-roh. So for our purposes right now, we are going to say A has no real solutions. This is where imaginary numbers come into play. So if I wanted to be able to categorize what A could be, if I allowed for this possibility where I could square root a negative, and that's what I is all about. I is the square root of negative 1. Can't hurt you guys to get a little preview. It is the only thing whose square equals negative 1. That is the way I is defined. The only thing whose square is negative. So that means here in my negative 48, I could split this as negative 1 times 48. The square root of negative 1 is now an I outside the radical. And then I could simplify the square root of 48. And so I'd get a plus or minus, and the i's, because it's always on the square root, always comes out between the plus or minus and the root. So not going to go through the whole thing, but if I simplified the 48, if I was allowing for complex answers, we would have plus or minus an I. The 48 is 4 times 12, but 12 is 4 times 3. So it's 4 times 4 times 3 under the radical. So that's 2 2's coming out or a 4 coming out. left over square root of 3. I know I just talked through a lot of that and hand waved it. If you'd like to see that, you can either check out the video on the radicals or come to office hours and ask. But for right now, this is what Alex should be asking this week. Next week, they may start asking for the I's, or it may just be on your college algebra homework. We'll see. It's hit or miss on the program whether it works right. Oh, I forgot. This one will actually do square root of 48. You could actually divide everything by 2 here if you notice it's all even. But I just habitually like to move things when I know I'm going to move them anyway. But I think that was because it was one fewer thing to write, because then I didn't have to write 0 over 2. There's that 48 I said we were going to get. And to get rid of the squared, we choose to apply a square root. We are applying it, so we put a plus or minus. I'm saying it that way because later on we're going to have equations where they start with radicals. Those don't get pluses or minus. What you see is what you get. These, since we're putting that in there, it gets a plus or a minus. Alrighty, so y equals plus or minus. Now we're going to break down that 48 and actually work through it. So like I said before, that was 4 dozen. And 12 is 4 times 3. Now, I see a pair of 4s here. I could circle those. That comes out. The 3 is left over inside. If you picked a different pair to start with, like you did 2 and 24, then you're not going to see a pair of 4s. In which case, what you're going to see is 4 2s and a leftover 3. I'm calling it a leftover because there's only one. So this pair of 2s is going to come outside the radical as a 2. This pair of 2s is also going to come outside the radical as a 2. This is not 22. This is 2 times 2. And then again, the 3 does not have a pair to satisfy the square root requirement, so it is stuck still under the radical. So the big thing is, if you take all the numbers you wrote down here after reducing a radical and they multiply back to that number, you didn't do it right. This product should now be smaller than that number. But really, you shouldn't be thinking about multiplying them all. I'm just saying that because some of you guys had that kind of problem on the midterm. So final answer, the 4 square root of 3 and negative 4 square root of 3, or the plus or minus 4 square root of 3. Again, if you ever have any questions, please come to office hours and ask. Now we get a little more interesting. We've got a squared thing instead of just a squared variable. I can still apply the square root property here. It's just going to look a little more interesting. Now over here, this one is like a little nicer because we're like, oh, 36, yes, perfect square, hopefully. So I already have the squared thing isolated, numbers on the other side. So I'm at the stage where I would choose to apply the square root to both sides. Now, as we progress through more and more college algebra topics, there are going to be more functions that we can apply to two sides of an equation. And some of them are going to have some caveats. But square root of 36 here is 6. And I put the plus or minus right then. Now you could split this right now, z minus 3 equals 6, or z minus 3 equals negative 6. Alternatively, and this is what you would get out of the quadratic formula, more or less, I add the 3, and when I do that, it's going to come here in front of the plus or minus. That plus or minus needs to be stuck to the 6. So I don't come over here and change it to a 9. I don't come over here and change it to a -3. I'm going to write here for an in-between 3 plus or minus 6. So that means we get 3 plus 6 is, here, let me do this, is 9. And then 3 minus 6 is -3. And those are our two solutions for z here. And if I take those solutions, as with any solution, I substitute it back into the original formula, I will get a true statement. In this case, I should get 36 equals 36. Because the other side had 36 and there's no variables there, so that won't change. So the left side has to end up equaling that. All right, let's take a look at crazy ugly mess over here. So if x plus 8 whole thing squared equals 24. Now, same song, second verse. We are at a stage where we may apply the square root to both sides. Just remember you're going to have a plus or minus. It's going to be x plus 8 on this side. And the square root of 24, 24 is 4 times 6. 4 is going to give us a pair of 2's, but the 6 gives us 2 singles. 6 is 2 times 3, not 3 plus 3. I know 6 is 3 plus 3, but when you're doing this factor tree, it's things that multiply. But sometimes we're a little stressed in the test and we panic, and sometimes we write 3 and 3 instead of 2 and 3. Because you're thinking, oh, it's a 3 and a 3, it's 2 3's, but your brain writes the wrong thing. Alrighty, so that pair is going to come out. Those are going to be left over and multiplied. So we have plus or minus 2 square roots of 6. Then if I minus the 8, again, that is going to go in front of the plus or minus. Writing it all together as one beautiful answer would look like so. -8 plus or minus 2 square roots of 6. And I believe once you start getting radicals in your answer, ALEKS will allow you to use a plus or minus. Not positive though, and different parts of ALEKS will do different things. So it just depends on which objective you're on and how far it thinks you are. It's kind of convoluted. If we had to write both answers separately, the first one would be written -8 plus 2 square roots of 6. Then make sure the comma is outside the radical. And then -8 minus 2 square roots of 6. So the -8 stays the same. It's just here from -8, I add however much 2 square roots of 6 is. And then I go -8, and then I subtract however much 2 square roots of 6 is. So what we actually have here are 2 points that are equidistant from -8. One's a little bigger, one's a little bit smaller. That idea is going to come up when we start looking at the graphs of quadratics. We're going to have a center line, and then all the points are going to be equidistant from whatever the center line is. And we're going to actually be able to complete the square to figure out the x number for the center line. It turns out it's actually just the outside part on the quadratic formula. All righty. One more with our square root property, about as ugly as it can get. Now, in the long run, once we have all of our tools, the completing the square and really the quadratic formula, I could just take d minus 4 squared, FOIL it out, bring everything over to one side, plug the numbers into the quadratic formula, I get the answer. Works every time. Will even work for complex. So if you only have to pick one thing to do, I would recommend getting really good at the quadratic formula, because if the answer is going to be ugly, that's probably the method you're going to end up with anyway. But here, since we don't have that yet, and because we have a thing squared and the rest of it is numbers, if you notice it, it will work and allow us to use the square root property. We end up with this. And now we're going to toss in square root over here, which forces a square root there and a plus or minus. So the square root of d minus 4 squared is now just d minus 4, and plus or minus the root of 12. So over here, 12, 4 and 3, which means we have a pair of 2's. 2 coming out, 3 staying in. So plus or minus, then the 2, then the square root of 3. So this is not 2 plus or minus the square root of 3. This is plus or minus 2 times the square root of 3. I say that because sometimes people they see the 2 comes out, but they put it in front of the plus or minus instead of behind it. And then our last step is to add that 4. And when we add a number over, that's when it goes in front, which is why it can get so confusing, because some things go one way, some things go another, and keeping track of which is which can be a pain. All right, so that is how the square root property works. For me, it's if you happen to notice you have a thing squared and the rest is just numbers, then yeah, you could isolate the squared thing and then square root both sides. Just don't forget the plus or minus. Now, what we're going to see in the next video next week deals with completing the square. And you guys could probably Google, there's plenty of videos with algebra tiles where you literally complete a square. It actually makes a square with the same length on both sides. So if you're a more visual, kinesthetic learner, that may be helpful to look up. So here's what we're looking at. So I want you guys to look at these two perfect square trinomials. X squared plus 14x plus 49. W squared minus 20w plus 100. And the factored forms are x plus 7 squared and w minus 10 squared. So what we want to observe is a relationship between this and this number, and then the relationship between this and this number. So I say it like that deliberately. There is an order to the way you look at these. Because if you glance down here, what we're going to do when we're completing the square is we are focusing just on having one, like x squared or a squared, w squared, whatever, and then a linear term, a term that has a variable but not to a squared power or anything. So if I only give you these two terms, can you figure out what that number is? So that's the pattern we want to look at. So whatever I do to 14 to get to 7, whatever I do to negative 20w to get to negative 10, that should work for every perfect square trinomial. And we can see that first step is divide by 2, and that gets us to what is in the factored form. We need to know both of these things. So we need to figure out what the number we need to add on is, and eventually we're going to factor it, so you may as well include that in the steps while you're doing it. I don't know if Alex asks you to write down the factored form. I would highly recommend doing so because that is where we're going with this. All right, and then from negative 10 to that last number, or from 7 to that last number. Well, 7 and 49, hopefully is ringing more bells. That is squared. And likewise, 10 to 100 squared. So first I divide by 2, then I square it. So if I call this a generic quadratic, now notice x squared w squared is 1x squared, 1w squared. We only complete the square when the square is 1 squared term. If it's not 1, then we divide everything by whatever it is, and now it's 1. Which can make for some really ugly looking things, but that's the way we do completing the square. Otherwise, it's a giant headache. So if I call this generic, x squared plus bx, then the factored form is going to be x plus whatever b is over 2, then that whole thing squared, and then what I put in the box here is half of b, or b over 2, and then I square that result. So that's how we'd write it as a formula. This goes here. So this is the term that completes the square. That is how many I would need to add in order to construct a square that is x plus b over 2 units wide and long. So same thing down here. W squared minus 8w. So the first step is divide by 2, figure out that factored form. So it is w, negative 8 divided by 2 is negative 4 or minus 4. So there's our factored form. And then to figure out what we would have to see here, the number that completes the square is negative 4 squared, which this is always positive, and in this case it is a positive 16. So both of those pieces, we're going to need both of them when we use completing the square in the next video. So I want you guys to get some practice with familiarizing yourself with, I've got these two terms, how do I figure out the factored form? How do I figure out what that number is? Because if I want to add 16 here in an equation, I would have to add 16 to the other side as well. So that's why knowing both is important. The next line, we want the factored form, but I need to know what number goes here because it's going on the other side as well. All right, let's take a look at our next one. So half of 2, well, that works out nicely. That is just 1. And then 1 squared is just 1. So most of the time it's bigger, but it doesn't have to be bigger, the number that we add to both sides. And in fact, you're going to see x squared plus 2x show up a lot. We tend to keep these numbers quite small, usually even, not always. And that is just to make our lives easier in grading and you guys in writing the answers. But it can get ugly. So we could have something like this with an odd number. We could even have a decimal or a fraction here, just as long as the squared term has a 1. All right, so half of negative 5 would be y minus 5 halves. And then the square of that, I'm going to write it That's the thing I want to add. This is definitely a time where I'm like, pull out the calculator. Don't stress your brain. So there's our factored form. The number that this equals, that would go on the other side, is 25 over 4. Because this thing is always squared, this is always positive. So the other side will also get added a number to it. All right. So what do these three expressions have in common? This is the thing I've already been saying. They all have a 1 on the squared term. In order to use this process, it must be a single square. No 2x squared, no 3x squared, no negative 4x squared. Got to be just 1x squared. So if I have x squared plus bx, the term that would get added on would be, I'm going to write it like this, because if b is ever a fraction itself, then seeing it as 1/2 times the fraction makes more sense than fraction over 2. So half of b squared, and the factored form would be x plus 1/2 b, whole thing squared. All right, so get some practice with that. So moving from these two terms to what do I add? What does the factored form look like? Gets more familiar, so that way that step isn't as boggling when we expand it out to how to use this to solve a quadratic. It can be done, and in fact is how we get the quadratic formula. So stick it out with me. There are some other uses for completing this square, which we are going to see when we look at circle equations. And as always, please attend office hours, ask me any questions you have about this or anything else, and I will see you then, hopefully.